Does anybody see? Okay. Okay, let's talk about something even harder. So we talked about constitutional isomers. We got that. We're good with that now. We talked about conformers. And we talked a little bit about stereoisomers with EZ. But there's also stereoisomers with sp3 carbons. So here's what I want everybody to do. Take one of the carbons from your kit and put 4 of the same size sticks in it. Doesn't matter color or anything, just 4 of the same size sticks. Okay. All right. Then I want you to, does everybody have an assortment of colors, I assume, in your kit? So take a one of the little hydrogen balls and put that on one stick. Take a red one on another stick, and a blue and a green. If you don't have one of those colors, use gray or something, or just an open stick. It's just so you have a different thing on each stick is what's important. Okay, everybody's got a different thing on each stick? If you are colorblind, leave one off so that you can distinguish which one is which. Or use one of the different shaped ones, or a couple of the different shaped ones. Okay. Now that you got that, either together with your partner or by yourself, set this down somehow. And imagine that it's looking in the mirror. Imagine there's a mirror next to it. And build another model that is its mirror image looking in the mirror. Here, I'll show you. Let me get mine started here. So I'm going to imagine that this one is looking in the mirror at this one, and I'm going to make the same thing on this side that is the mirror image of the first one. So it looks something like that. So they all kind of line up as though one of them is looking in the mirror at the other one. Everybody's got that? Okay. Okay, so here's the question. Are they the same? I mean, they look pretty much the same, right? But you can probably tell by the way this is going if they're not actually going to be the same. So pick it up, pick one of them up, and rotate it, and try to line it up exactly with the other one, and watch what happens. You can get two. You should be able to get 2 of the substituents to line up, and then the other 2 are flipped. See that? Yeah, twist one of yours around and see if you get it to line up like that. Yeah, so do you see how they're not the same?
Oh, okay, I guess they are not the same.
Everybody convinced that they're not in fact the same? See how you got the red and the blue lined up. You can't line up.
Oh, that is my fault.
Yeah. Anybody else have trouble seeing this? Yep. So then if you try to line them up exactly, you can't do it. You can line up 2 of the colors, and the other 2 colors are not the same. No? Just try to line them up. Try to put one right on top of each other. See how they don't actually line up? You see it? So these are not the same. These are actually stereoisomers. This is a different type of stereoisomers. These are obviously connected the same. You got a carbon in the middle, and you got whatever these other things are connected to it. They're connected to the same things, but because of the orientation in space, they're not actually the exact same structure. They're stereoisomers, right? So we're going to draw this. So pick one of them. And the way we express this on the screen is by using that dash wedge notation. So if you want to keep it the same as I have mine, you know what? I need a green pen here. Just a second. Let's see how I do that. I don't know how to add a green pen to this. All right, well, I'll have to figure that out. I don't have a green pen, but we'll make it work. Okay, so I've got my carbon. We're going to call this one a carbon, and I'm going to keep the round ball up top.
How are you holding yours? Because I want to drop mine like yours, but
Yep.
I want to see how you're holding it.
So I'm going to hold it with the round ball on top,
Yeah.
and the green one, since that's the one I don't have the color on, I'm going to have that coming straight out to the left, and then the red in front and the blue in back. So I'm having my green one. I'll just say G for this one, even though I don't have the color for it. And then on the other side, I've got my red coming out and my blue going back. So between the two that you've made, if you want to follow along exactly with what I have, one of yours should be able to have that orientation, and one of them should not be able to have that orientation. So the mirror image of this one is the other one that we built. So if we imagine this thing looking into a mirror right here, on the other side of that mirror should be something that looks like this. So the ones that are directly opposite have a counterpart on the other side of the mirror. So you should be able to see that or whatever you've made. Similarly, you should have your structures there, and you should be looking at shapes that mirror what is on the paper. All right, so the way that they're drawn here, it's easy to see that they're mirror images, but it's not easy to see that they're different. They look the same in this orientation. So the other thing we want to do is rotate that structure on the right. Let's rotate that structure 180 degrees and redraw it. So if we turn this around 180 degrees, we get, and you can physically do it with your model. This is why models are helpful. The top stays the same because we rotated it around the top. Now the green one is off to the left, and the blue one is coming out, and the red one is going back. Oh, I get my colors back here. So I hope you can see that with your models. Ideally, a goal here is that you can do these kinds of manipulations in your head and on paper without looking at the models. So imagining what it would look like if this thing were to rotate 180 degrees. The thing in the back comes around to the front. The thing in the front goes around to the back. We also are going to work on what happens when you rotate them in other directions. So flipping it down from top to bottom or around to the side. All right, this brings us to our first definition around these things. and that word is called chiral. Chiral is a description of any shape that has a non-superposable, sometimes called superimposable, mirror image. So a shape is chiral when its mirror image is not the same as itself. It's a way of describing symmetry. The word actually comes from Greek for hand, so it refers to handedness. Because, of course, our hands are chiral, and that's kind of the classic definition, or the classic example, that your left hand and your right hand are mirror images, but they are not superposable. They're not the same. You can't make them line up, just like we did with those molecules. Okay. The opposite of chiral is achiral. So a shape that is achiral, the mirror image is the same as itself. So our whole body, and really anything with bilateral symmetry, anything that you can draw a symmetry line in the middle of, is achiral, because its mirror image will always be the same. Assuming that we're perfectly symmetric, which is not quite true, but close enough. Okay. So where does this come from? A common source of chirality in molecules is Stereocenters, which are sp3 carbons with 4 different groups attached. Okay, so if we go back to our models here, if we took off the green and the red, we now have carbons that have 2 of the same things attached, these open sticks now, and then 2 other different things attached. And now if we look at those mirror images, and we try to line them up, they are actually the same. So that chirality is lost. These are achiral, because their mirror images are actually the same. And you can see that symmetry again. If you look kind of this way, these are symmetric molecules. So now those are no longer chiral. So if we're looking at a larger molecule, it's really not feasible often to like draw the entire mirror image of a large molecule and then flip the whole thing around and see if it lines up or not. So a way that we look for stereochemistry, that we look for chirality, is by looking for sp3 carbons where everything is different. Everything attached to those carbons is different, so 4 different pieces. All right. So let's look at an example of where we might find that. So here's a structure. Okay.
So after we took off the colors,
Yes.
would then this be achiral?
Correct. Yep. So it's no longer chiral then. All right, so if we look at a molecule like this, how can we find chirality in a molecule? So here's a molecule of lactic acid. And we can look at the different, and what you would do first is look at the different carbons in the molecule and see if any of them have 4 different groups attached. Any of the sp3 carbons have 4 different groups attached. So does anybody see a stereocenter in this molecule? A carbon with 4 different things attached? 4 different groups in general. And when I say groups, I mean the same priority rules that we used for E and Z. The double bond here, you mean this carbon?
Yeah.
So this carbon can't be a stereocenter because it is not sp3 hybridized. So, and the reason that's important is that sp2 carbons are flat. So they always have a symmetry plane cutting right through the middle because they're planar. An sp3 carbon is tetrahedral, so it doesn't necessarily have that symmetry the way a flat planar sp2 carbon would. Lisa?
Is it the one that's underneath OH?
Yes. So right here is a stereocenter, meaning a center of stereochemistry, something that could potentially be higher. Now, in the way that I've written this structure, I have not specified which type of arrangement this is, which type of orientation this is. But we know that there are 4 things attached there if we include the undrawn hydrogen that's also there. So we could draw this as a stereocenter by specifying one orientation or the other. So let's do that. Usually the easiest way to do this is to leave sort of the main chain area alone and then add the dash and wedge notation to whatever's coming off of it. So OH and H. And then there's another one where that would be flipped. And those are not the same structure. Those are these non-superposable mirror images. Now that structure, we could do the same exercise with it. We could build a model of it. We could look at one versus the other. We could line them up to make sure they're mirror images. We could, flip them around to make sure they're not superposable. And it would all work just the way we did before. But as the molecules get bigger, it's a lot easier to just look for those stereocenters. If you see those sp3 carbons that have those different things attached, then we know there's a source of stereochemistry there, and these are likely to be chiral. Oops. How do I fix that? Okay, sorry. Okay. No, still not doing it. So the relationship between these then has its own special name. These are called enantiomers. Enantiomers are non-superposable mirror images. So if you have a chiral molecule, that means that its mirror image will not be the same, will not be superposable, and therefore those two molecules are enantiomers of each other. Enantiomers are a little bit special because they're completely opposite, but only in terms of their three-dimensional orientation. So like physical properties of enantiomers are usually identical. They'll have the same melting point and boiling point, they'll have the same polarity, they'll often react in similar ways. The only way that this difference becomes important is when they interact with other chiral molecules, and specifically for our purposes, our bodies. All the important building, not all, but most of the important building blocks of our bodies are chiral molecules. Amino acids are all chiral, which means proteins are chiral. Sugars and carbohydrates and starches are all chiral. Many of the other molecules involved in our bodies, enzymes and lipids and things like that, also have chirality. So when we're talking about things like drugs, pharmaceuticals that we want to introduce into the body, or just different processes, physiology and stuff, this idea becomes really important because one enantiomer might do a thing and the other enantiomer doesn't. Or worse, one enantiomer might do a good thing and one enantiomer might do a really bad thing. There are some examples of that in history. For instance, there was a pregnancy morning sickness drug in the 70s, I believe, called thalidomide that was an anti-morning sickness drug, but ended up causing really bad birth defects. And it was because of this idea of chirality that one of the enantiomers did its thing and the other enantiomer was causing the birth defect. But because they're so similar, and in that molecule, actually they would interconvert automatically, it was impossible to separate them. Enantiomers are often really difficult to separate. Another example, a modern and less terrible example, is there's an allergy medication called Zyrtec, very popular over-the-counter allergy medication. And there's another medication called Xyzal. I don't know if you've seen that one. So they're the same. Xyzal is a purified single enantiomer, whereas Zyrtec is the mixture of both enantiomers. But in that, I believe that in that particular formulation, only one enantiomer is actually active, but the other one doesn't do anything. It just doesn't do anything. So they're able to get a patent for the purified one, but they actually both do the same thing. So this kind of thing comes up because of how it interacts with other chiral things.
So only other chiral?
I mean, only is always a tricky thing with chemistry, but generally that's where you see those differences.
So when they're reacting with a chiral thing, it's same,
Right.
it doesn't change.
Usually, right.
Okay.
What can happen is you can take something that's achiral, and you can use a reagent that is chiral to turn it into something chiral that you want it to be. Turn the achiral thing into something chiral the way you want it to be. So like if you want the OH on the wedge in your final product, you use this other chiral thing to help like force it to do that. Yeah, that kind of stuff. All right. So this is the part you're all going to really like. Excited? So how do we tell these from each other? If we're naming compounds, these would both, kind of like the double bonds, these would both have the same name because they're all connected in the same way because they're not constitutional isomers. So we need a configurational assignment like E and Z for these kinds of things. Shaking your head like, no, we don't. Like, no, we really don't need to do that. No, we actually do. So the good news is that we already know how to do this because it follows the same kinds of rules as this one. So let's try it. Okay. Let's take a look at this molecule. We would call this 2-fluoropentane. But since there is a stereocenter at carbon number 2 there, 4 different things attached, the F, the H, a CH3, and then a CH2, CH3, that makes that a stereocenter. We often designate stereocenters with a little asterisk or star. So that's a stereocenter right there. And that means that 2-fluoropentane is not a specific enough name because whether that F is on the dash or on the wedge actually makes a different compound. This is the enantiomers. So we need a designation for how to assign this, and here's how it works. First, let's write this down actually. first we're going to orient the molecule. Well, no, let's not do that. Let's not do that. That's hard. That's how the book says it, but it's a little harder. Let's do it a little easier way. So first we're going to assign priorities. So we look at the stereocenter, we look at the things attached to it, and we assign priorities using those same rules that we used for the double bonds, the Kahn-Ingold-Brelog rules. So what has the highest priority of the four things attached there? F, yes, fluorine. So that's number one. What has the lowest priority? Hydrogen. So those are the easiest to find. And then we look at the other two, which are carbons. Between those two, what has the higher priority? The left or right? The right has the higher priority because we go carbon, and then there's more carbon on the right, but there's only hydrogen on the left. So this is number 3, and this is number 2. So that's our 4. So instead of just assigning 2 priorities, 1 and 2, higher or lower, we have to assign all 4 priorities. Okay, we got our priorities assigned. So then second, or we orient the molecule so that the lowest priority is in back. And when we say in back, we mean on the dashed bond. So it's going away from us. Now I'm going to give you a trick for this in a little bit because this could be tricky. You know, you have to like flip the whole molecule around or do whatever you need to do to put that fourth one in the back. In this particular molecule, this first example, it's already in the back. See that? Hydrogen's already in the back, so we're good. Okay. I don't like that word read. Let's say we move around from 1 to 2 to 3, and depending on which direction we go, that assigns it as either right or left, which the values we use for that are R or S. So it looks like this. If we're going around this way, from 1 to 2 to 3, that's like making a left turn in the car. Everybody here know how to drive? Have driven a car before? Right? So that's a left turn. So we call that S. It's actually Latin for left. And if we go the other way, that's a right turn, clockwise, and we call that R. So let's try it back on our molecule here. If we go from 1 to 2 to 3, which direction are we going? This way, right? 1 to 2 to 3. So that's a... Which way are we turning the car? Right turn. Right turn. Everybody see the right turn? 1 to 2 to 3. It's a right turn. Okay? So that's R. So that means that we can add to our name and we can call this R2-fluoropentane. Okay, let's try the enantiomer now. We already know what it's going to be, but let's look at how we get there. So we're going to draw the mirror image of this, the opposite, but we're going to do it in the easier way. So instead of imagining a mirror and then trying to get everything to line up, we're just going to flip the F and the H. If we've already assigned one of them as R, We know that when we flip it, it's going to be the opposite. So it's going to be S. We already know that. But let's see if we can go through the motions and get it to work. So we're going to assign our priorities first. Priorities stay the same. 1, 4, and then 2 and 3.
I don't know which way to look at it because I'm having compulsion to look down this way.
What do you mean down it that way?
Like to draw it, like they're looking at each other lengthwise, which I guess would end up the same.
You mean the dash and the wedge?
To have my one start, like actually like it's looking at, to have my one start on the other side, right?
I guess I don't understand what you're asking still.
I guess, I think it's just because you're doing it maybe up on top, so they're doing.
So the straight lines are in the plane of the board, and the dash and the wedge are coming out and going back. But what those are really showing are two things that are taking the same space. So, for instance, let me show you this. Let's say we have this, and that's like our regular chain. So the green is on the wedge, and the blue is on the dash. And we write them on paper separate from each other, like side to side. But in reality, we're assuming that they're actually directly in a line, front to back. So by drawing it like that, I'm saying the H and the F are lined up in a line. They are exactly in
Why
the
would
same
you draw the
place.
H and F on the right side of the second drawing? I think that's what's.
So you mean the H on the right and the F on the left?
The whole thing, the long tail to the left.
Oh, we can. So that's actually what we're going to do.
Why wouldn't you do
Next.
that? We wouldn't.
So the reason yeah, that's fine to do. There's nothing wrong with that. The reason I didn't is because this way we can clearly and quickly see that those two structures are stereochemical opposites, because the top one has the F on the dash or on the wedge, and the bottom one has the H on the wedge. So they're like right on top of each other. You can see that the dash and wedge are opposite.
Okay.
But what you're doing is exactly right, because this is what we're going to have to do next. If we look at number 2 in the steps, number 2 says orient the molecule so the lowest priority is in the back. Right now, the highest priority is in the back. So what that says is we need to flip this molecule over so that instead of the H coming out at us, the H is now going to go back. And this is the kind of thing that is really helpful to do with models at first until you kind of get the hang of it. So we want to flip this whole thing around 180 degrees. And the result of that should be this. If we flip that thing around, priorities are the same. 1, 2, 3, 4. But now if we do our steering wheel from 1 to 2 to 3, we're going this way, which is a left turn. And so that's S. So that makes this S2-fluoropentane.
Would this be achiral or?
No, this is also chiral. These two are enantiomers of each other. One is R2-fluoropentane, one is S2-fluoropentane. So we've got a, yeah, question.
What's the benefit of the middle step? What's the benefit of?
As the molecules get bigger and bigger and bigger, it becomes easier to simply switch the dash and wedge than to like flip the whole molecule around. But it's always, it doesn't matter. If that works better for you, you can always do that. So here, this kind of goes along with this trick. If I gave you this structure right here, and let's say it was some big complicated thing, and you wanted to assign the stereochemistry, the correct step-by-step way to do that is to assign the priorities and then flip the whole thing around so that number 4 is in the back. But notice what would happen if we leave number 4 in the front. If we go 1 to 2 to 3, we would get R, right? And that would be wrong. So what we can say for kind of a shortcut is, if the 4th priority is in the front instead of the back, we can just do the opposite. So instead of, if we go this way, or sorry, what was it? If we go this way, instead of calling that R, we just call it S. We say, okay, we know because the 4th priority group is in the front, so it's just going to be the opposite of whatever we find. So if the 4th priority is in the back, we go with what we find. If the 4th priority is in the front, we do the opposite of what we find.
So if the 4th priority is in the front, instead of doing the flippy thing on the bottom, we can just go 4, 2, 1 backwards to make the
Yeah, yeah, 3, 2, 1. Yeah, we'd still ignore, or we'd go 4, 3, 2. We'd ignore the one in the back. Mm-hmm. Here?
Yeah.
Because that's the Stereocenter. That's the one that has the orientation. So if this were a Stereocenter here,
Yeah, or like if you were like just like
mm-hmm.
that's
Yeah, also carbon. Yeah. So if this middle one were your Stereocenter, this side would have higher priority than this side because of the F.
Yeah.
Yeah. All right, and then so we're out of time, but next week we'll continue with this. We'll talk about what happens when that 4th priority group is not on the dash or the wedge, and some other relationships with stereochemistry. So this takes practice. Grab some models, work through some problems, practice this orientation thing. You'll definitely get it, but it takes a little practice. All right, and I'll see you over in lab. A stereocenter is any sp3 hybridized carbon that has 4 different things attached to it, 4 different groups, as defined by the priority rules.
Wait, 4 different groups. SPC. Okay. Okay, got that. So
Mm-hmm.
this okay. So like this view.
Yeah, so the way you drew it is not right, because those are the same.
Okay.
Maybe I drew it wrong too. Yeah, see how I have the OH and H on opposite things? So they should be opposites. That's what that is.
That makes much more sense. Okay. So they're like, wait, so the antibars are pink space,
Yep.
antibars